We can also conduct hypothesis tests for population proportions. And testing for proportions for managerial decisions is quite common. Our aim is to identify whether or not a proportion, which is sometimes given as a percentage from some sample, matches a defined or prescribed or proportion or percentage that is either known in industry or that is known either experientially or something that we wish to test for. So here are a few examples. We developed a survey and we identified that 18.2% of our respondents are Hispanic. And we wish to see if this percentage matches the U.S. Census proportion for the population of Hispanics in the U.S., which is 17.6 as of Census 2015. Another example might be that 500 students at a university took an exam and 75% passed, and we wish to see if this is better or worse than the national average of 71%. In addition, we might say that a survey of voters was conducted on presidential approval, and the analyst wishes to ensure that the proportion of Democrats in the sample matches the national proportion to ensure validity of a test. So for this hypothesis test, when we're doing population proportion, remember, we're going to be focused on the Z statistic, and because we're using population proportion and our sample sizes are going to be very large. So here's an example from the first bullet point that we had on the previous slide. We want to see if our marketing survey accurately represents a demographic. And we know from the census that the Hispanic population is 17.6. Our survey has a Hispanic proportion of 18.2%. So let's see if this matches our population proportion. So what we need to do is calculate the Z statistic, which is given here in the middle. And it is basically the difference between the sample proportion and our estimated proportion, which is known as P0 or P0. We take that value, put it over the square root of the P0 value, which is the population estimate that we're looking for, times 1 minus P, again the percentage of not being Hispanic, divided by the square root of N. On the left side, we set up all of our values. Our P hat, which is the estimation that we had calculated from our sample as 18.2%. Our P0, which we're going to test against, is 17.6. We have N of 500. We had sampled 500 people in this survey. And we set up our hypothesis test right below it, which is P hat equals P0. That's our null hypothesis. And our alternative hypothesis is that P hat is not equal to P0. All the way on the right, we calculate the Z statistic, and we just plug in the numbers. We have 0.182 minus 0.176, all over the square root of 0.176 times 1 minus 0.176 divided by 500. And we end up with 0.006 divided by 0.017, which equals 0.352. What we're going to do is, in order to calculate the p-value, we will actually need to take 2 times 1 minus the norm S dist 0.352 with a cumulative true. And this will give us 0.725. So let's explain what's happening. The norm.s.dist function will give us the area under the curve at 0.352 all the way to the left. So it's giving us everything from the left side of the curve to 0.352. Now, what we're going to do is we actually want the right tail first. So in order to do that, we will actually need to do 1 minus so that we can get the area of the curve on the right side of this 0.352. The reason we multiply it by 2 is because the area on the right tail will be equal to the area on the left tail. So we multiply it by 2 to figure out what the probability is, or the area under the curve, of being on the right side and the left side tail of an equal distance. So since we've calculated that it's 0.725 and it's greater than 0.05, we cannot reject the null hypothesis, and therefore we can say that the sample proportion matches the population. Remember that in this test, because it's an equal sign, and we saw this from a previous module, this is a two-tailed test. And it's important to know that so that we can determine how we utilize the norm.s.dist function. So remember that the Excel only provides a norm.s.dist Whereas before, when we were doing a t-statistic for a sample mean, we had a two-tail test. We actually had the norm. We had the t.dist.2t test that we could use. So first we have to figure out what's the difference between the tails and when do we use them. And it does take a little getting used to, but it's similar to the module that we had before. But here, remember that the norm.s.dist function provides the area under a curve of a normal distribution. Okay, the full area will be from 0 to 1. So 0.72 means that 72% of the area under the curve falls from that point to the left. So the norm.dist function provides the area under the curve to the left of the point provided. Now, in the example to the right, if we were to use that line, we would, where it is for 72% of the curve, we would want to find the z-score. Now, we could use the norm.inv to actually take the 72% and plug it in, and it would give us a score of 0.58. So if we did norm.s.0.58, that would give us a cumulative area to the curve of the left of the z-score. So that line, that dashed line, represents 0.58, and 72% of the curve will lie to the left of it. And again, we can do the inverse process of doing norm.inv with a percentage of 72%, or 0.72, or more specifically 0.719, and it will give us a z-score of 0.58. Remember that the purposes of calculating the z-score is to get a standard number so that it can be compared to something else. In this case, we're comparing it to a perfect normal standard distribution with a mean of 0 and a standard deviation of 1. So therefore, a z-score of 0 will match the exact middle of what we're looking for, and this would be the mean and the median. And that's why we're calculating it. So when we calculate our z-score here of p hat minus p0 over the square root of p0 times 1 minus p0 divided by n, when we do that, we're going to get a z-score. And you can see that if the proportion estimate p hat is equal to p0, the numerator, the top, would be 0, and therefore our z-score would be 0. And so that means it would lie directly in the middle and that they would be equal. And so therefore that would be an indication that we should not reject our null hypothesis that the two are equal. And the further away p hat is from p0, the larger or smaller that numerator becomes, and therefore that the z-score will follow suit. And so the z-score is really giving us a measure of how far away from the mean we are. And if you recall from previous modules, it's actually giving us the number of standard deviations away from the mean. So if we want to know if a population proportion or mean is equal to a given value, we'll need to test both sides, the left and the right tail. Again, because we're looking for equality. If it's equal to, it should be very close to the mean on both the left and the right side. But since Excel only gives us a function for the area to the left of the curve using a standard normal distribution, we have to do a little math. If testing for the two sides at the 0.05 significance level, it means that we're looking for a p-value of the area of the curve at that level. It means that the total area on the right and the left will be equal to 0.05, which means that we're actually going to be doing 1/2 of the area under the curve, because the total area is 0.05, so that means each tail will be 0.025. And so therefore, if we're looking at the right side over there and we're looking for the right tail, its actual area would be 0.975. The function will be from that point all the way to the left, which would constitute 97.5% of the area of the curve. So therefore, if we really want the tail, what we'll need to do is we'll need to do 1 minus 0.975, which is 0.025, to actually get the z-score that we're looking for. Now, if we want the left tail, we could actually use the negative z-score of negative 1.96 to actually give us the result. Or we could do 1 minus norm.s.dist of the positive 1.96, and we will get the same answer. Therefore, we have some following rules that will probably help. If we're looking for a two-tail test, the Excel function that we're going to use is 2 times 1 minus the normal standard distribution of a given z-score, taking the cumulative true. Now recall that the normal standard distribution with a z-score of true will give us everything to the left of the curve. So 1 minus that would actually give us the right tail. The reason we multiply it by 2 is because it will give us both the right and the left tail, the area under both sides of the curve. The left tail, we would just do norm.s.dist z-score, again true for the cumulative distribution, because that will give us everything from that particular z-score all the way to the left. So in the example below, if our z-score was negative 1.96, it would give us the left tail directly of 0.025. If we're looking for a right tail test, we would take the z-score, put it into the norm s-dist function, and again, that function by itself would give us everything to the left, so by taking 1 minus that, it would give us the area of the curve to the right. Now let's take a look at one of the one-tail tests using the same example that we had before. What we're doing is we have the same z-score that we had. Everything is the same except our hypothesis test down below is slightly changed. We've changed our p-hat, we've changed our null hypothesis to be p-hat less than or equal to p0. So the estimate we believe is less than or equal to the actual population estimate. And our alternative hypothesis that we're testing against is that that's not the case, and that our estimate is greater than the population proportion. So we calculate our z-statistic in the same way, and we end up with 0.352. Now again, since the alternative hypothesis is a greater than sign, we're going to be looking for a right tail test. So we put in the 352 into the norm s-dist function by itself, and that would give us everything to the left, the area of the curve to the left. We will do 1 minus that so we could get the area of the curve on the right, and we end up with 0.365. Since the p-value is 0.365, we cannot reject the null hypothesis, and therefore we can say that the sample proportion matches our population proportion.